of the morning session. So Thomas Kare will continue with the description.
Yeah, so hello. Okay, welcome back. So I will today continue to talk about binomial ideals, but now about the non-prime binomial ideals. So now we're talking about decompositions of binomial ideals and what those might have to do with applications. So 3 is binomial ideal decompositions. And by decomposition, I always mean an intersection decomposition. So you might, if you have studied commutative algebra, you might have seen this. I hope that at least some of you have. So if I, this is a useless modifier, every ideal in our polynomial ring has an intersection decomposition. So decomposition here means to write your ideal as the intersection of larger but simpler ideals. And it's called decomposition because on the geometric side, it decomposes the variety into parts. I is equal, each ideal I is equal to an intersection I Qi, where Qi are primary ideals. So this is a very nice story in commutative algebra. It generalizes the factorization of numbers into prime numbers, which we all love and learn about when we learn about numbers first. You cannot have all the wishes come true. So I is not a product of prime ideals, but instead it's an intersection of primary ideals. So intersection is a generalization of product, and primary ideal is a generalization of, well, it's a generalization. It's a slightly weaker concept than prime ideal, but it's at least good enough to do this on the geometry, to do the right thing on the geometric side. So then, for example, the variety of I is the union of the varieties of the Qi, and those are all irreducible varieties, meaning that they cannot be written as a finite union of strictly smaller varieties. I mean, there are many subtleties to this. Some of these things might be redundant. So this union here, and so these are not exactly the parts of which this V is contained. So there might be some redundancy in here. The decomposition into these Qi's is not unique, although the decomposition into irreducible parts is, of course, unique. But I don't have the time to give a commutative algebra lecture about primary decomposition. So I want to focus on applications of this to binomial ideals. So first of all, you might have some questions. If this is a binomial ideal, can I always have it that these Qi are also binomial ideals? The answer to this is directly no. If you think about it for 5 minutes, you will see that factorization of polynomials is a special case of this primary decomposition. And if you have the polynomial x cubed minus 1 in Q over Q, it cannot be factored into binomials. Obviously, over C it can. And the theorem of Eisenbart-Stumpfeld says that over C or any algebraically closed field, a binomial ideal has a binomial primary decomposition. I will talk more about this theorem in my tomorrow's lecture, because what I don't like about this theorem is the algebraically closedness assumption. So I will talk about alternative decompositions that work without, that also decompose into binomial ideals, but work without this assumption. Okay. So today, we want to use this to analyze walks very similar to the walks that we studied with Markov basis, but we don't have a Markov basis. So we're gonna analyze non-connected walks for their connectivity. And I'm gonna set it up in a slightly more general setting. So assume B is some set of moves. You can think about them as moves. I will formulate my problem with graph theory. So I will put this in Z to the N now is some set of integer vectors is given. So very much in the spirit of yesterday, this defines a graph on n to the n. So this on n to the n means that's the vertex set is this commutative monoid, and the edges are going to be the elements of B, and I place them wherever they fit. So where U is a neighbor under B with V, if their difference is in B, or say minus B. I will make B smaller by writing U minus V is in plus minus B. And the general class of problems that we're going to talk about is studying the connectivity properties of this graph. Studying connected components of such graphs, of this graph appears in applications such as integer programming. That was the optimization. In integer programming, you might even be interested in the directed version of this, because integer programming is optimization. You might want to make a directed graph. We'll keep it simple now and work with the undirected graph. I already mentioned in my first lecture this combinatorial game theory. Game theory, where you have board positions or game positions, positions in which the combinatorial game is, can often be encoded. If it's a combinatorial, a discrete game with only discrete information, you can encode the game positions as the integer points in this monoid. So game positions are in n to the n, and rules or moves you can make, the rules are encoded in B. And now it makes even more sense what I said on Monday, that you want to maybe analyze, can I reach a winning position from the position I'm in using the moves is a connectivity property of such a graph. Okay, and then something I very much like, but since I don't want to run over, I will only say it verbally, is that I started this itemized list there and it's not enough space, so I will continue it over here. So it's another item. Complexity theory of computer algebra and commutative algebra. Complexity of commutative algebra. So in the long ago, 100 years ago, do I have the date here? Grete Hermann proved that if you have an ideal I that's generated by F1 to Fs, and you have an element G in there, then you know that G can be written as a sum over Hi, Fi, with Hi some coefficient polynomials. Of course, that's the property of being in the ideal. And the complexity questions about commutative algebra can often be boiled down to understand how the degrees of the Hi relate to other invariants that you have in this situation. The number of variables of the polynomial ring comes to mind, the degrees of the Fs, and the degree of G, of course. So, and 1920 something, yeah, not right, it's on 1926. 98 years ago, Grete Hermann proved that the bound that the degree of hi is at most doubly exponential in the number of variables. 1926, Grete Hermann proved that the degree of hi is at most something plus the something. Okay, the something is just a d plus s d to the 2 to the n. Yeah, s d to the 2 to the n, where d is the maximum degree of the f's. D equals max degree of f's. Or was it the degree of d? Sorry. Now I'm confusing myself. Okay, anyway, so this is not so important. The important part is that this bound is doubly exponential. Doubly exponential is bad. Yeah, so very high degree might be necessary. So everybody thought, okay, that's like the first upper bound. There's a crude upper bound. Okay, you have an upper bound, we'll find a lower bound, then we improve it step by step. Yes, we meet somewhere with exponential. And so this was, so David Mumford, for instance, the algebraic geometer, Fields medalist, was convinced that this bound is not sharp. But in the 1980s, so 1980s, so much later, two computer scientists, Meyer and Meyer, spelled differently, proved that the bound is in fact sharp. And the proof that this bound is sharp, called the Meyer-Meyer ideals, involves ideals that are constructed using combinatorics of graphs. I mean, their method of proving is importing computer science hardness results that were already known about certain, you know, they have all these different models of computation, token machines that move things around on a graph, to implement it in such a situation, translate it into binomial ideal, and get this commutative algebra result. Yeah, so there's this, I like this paper a lot, Meyer ideals show it is sharp. It's very much to the surprise of the algebraic geometers. But then the algebraic geometers fought back. So there is now results that, I mean, it has led to very deep understanding of why this terrible behavior is never observed in algebraic geometry. When you do actual computations in algebraic geometry. So the Gröbner basis seemed like a theoretical concept because of this result. The computer scientists, they would have never implemented Gröbner basis because they thought it's nonsense to implement such an algorithm with such complexity. And then Mike Stillman and the algebraic geometers, they said, well, this is not our experience. Our experience is that the computations that we want to do, they work really well. And so they started Macaulay 1. So Macaulay 1 was out of this spirit. And then it was a big success. And now these concepts like regularity, Castelnuovo-Mumford regularity that we study, they try to express that they came out of the desire to understand what is the property in algebraic geometry that prevents us from this stuff happening. Yeah. Okay, and it has this connection to binomial ideas. Okay, now I took like some time, but I like the story very much. Yeah.
This is the same paper with the title, what can be computed.
So Mumford didn't believe it. And then apparently the story goes, it was before I was born, yeah? So or maybe shortly after. I was in elementary school. There was an Oberwolfach meeting where Meyer and Mumford meet and they clarify the remaining questions. Let's say put it like this, and then Mumford together with Bayer and Stillman, or just Bayer, David Bayer wrote this paper. What can be computed in algebraic geometry? It's one of my favorite papers. Everybody should read it. It explains Gröbner basis from a geometric perspective, and it takes this. It takes you through the process how the Fields medalist like tries to understand this this new bit of information that he got.
So there is one paper by Meyer and Meyer. It's what can be computed in commutative algebra and algebraic geometry. Then you're talking about the same.
No, this one is called commutative semigroup. The original reference where this result is in, where I have it cited, the complexity of the word problem for commutative semigroups and polynomial ideals. Advances in Mathematics, 1982. Reference MM82 in my notes. Yeah. The relation is you might become an idea of the relation in the next half hour, but it's of course it's more complicated than just. So the relation is that connectivity in these graphs has to do with containment. Okay. Let me write that proposition that makes one connection. Wait, Cayley graph. I mean, Cayley graph is something different. Cayley graph is you have a group, you have a generating set, you have a presentation of a group, and then you have the group generators acting on the. But this is not. I mean, this is not the Cayley graph of a monoid because the graph. So my working example will be let's look at the example. Let's say B consists of 2, -2, and 3, -3. So then we are in N2. We can make a nice, my favorite picture, as I like to call it. Okay, except that I have to do these dots all the time. Okay, let's draw the graph. We have the green edge. Green is bad. We have the blue edge. Maybe blue is also bad. Blue, okay? Can you see blue? Okay. So blue connects anything that has a difference of 2 - 2. So in the bottom here, this is just, it doesn't fit in. Yes, the what's connected is 2, 0 to 0, 2. So it makes a connection here. And it makes a connection here, and here, and here, and here, and here, and so on. Yeah. I fit it in wherever it fits in. So 3 -3 is even longer. So the first time it appears is here, and the second time it appears is here, and the third time it appears here, and so on. So you can study the connected components of this graph by looking at the picture, but of course I'm going to tell you how to do it with the binomial idea. So by looking at the picture, you see there are these isolated points, 1, 2, 3, 4 isolated points. And then these two are connected. There are 2 points that form a connected component. And from then on, it's just degree by degree. Each degree from 3 on is 1 connected component. Yeah. So here the blue ones still make 2 connected component in degree 3, but by the yellow edge they are connected again. So starting from degree 3, it's just 1 connected component per degree. That's the answer to the combinatorial problem. And let's see how we can do this with binomial ideals. Okay, so we need a proposition that's very similar to the fundamental theorem of Markov basis. So from B, we construct a binomial ideal as we've always have been doing. IB be the ideal generated by x to the b plus minus x to the b minus for B in our set B. And then U and V are in the same connected component if and only if the corresponding binomial x to the U minus x to the V is in that ideal. Okay, so the proof is very similar. You express a walk in that graph. If they're in the connected component, you express a walk as the sequence of modifications to x to the U that get you to x to the V. It's written up. There are references in the write-up, and you can check it out. The crucial idea now is to decompose IB to get a list of necessary conditions that are jointly sufficient. Idea, decompose IB to get necessary conditions that are jointly sufficient, okay, now comes the part where we have to do the primary decomposition of this ideal in our minds. It's the hardest part. So in the example, let's see that we get the same thing, yeah? Or that we get information about this. Okay, this hinges, of course, on the premise that the QIs are somehow simpler than I. But this is like general spirit of commutative algebra. You decompose I in a primary decomposition to make things simpler. So the QI are going to be simpler. So we hope that this is actually useful. It's actually useful if it's easier to analyze the connectivity for the graphs that come from the QIs. So in this case, IB is equal to x squared minus y squared and x cubed minus y cubed. Okay. First question, is this a prime ideal? We're working over, let's say we're working over Q. I like Q, computable field. I like computable fields. Who knows the binomial theorem for degree 2? Yes? Okay, so this factors is not prime. So here's the proof: x minus y times x plus y is equal to x squared minus y squared. So there's one. So now if you go more into primary decomposition, you know that there are these splitting lemmas. So there will be one component with which, so let's take this factor x minus y. There will be one component where x minus y is nilpotent, and if it's prime, where it's 0. Whereas in the ideal, and one component where will be non-zero divisor modulo that component. So certainly there will be a component where x minus y is contained. So, and in fact, well, that's a pretty big ideal already. It's prime. And well, the other component, I computed it for you, is generated by x. Wait, do I want squares or cubes? Now I have to look myself. Here is a cube. Is that what you mean? Yeah. But the monomial ideal here has squares. Yeah. Okay. So, okay, maybe we make that an exercise. How to do this on paper. Of course, what you can do in Macaulay 2, you can take this ideal and type colon this. Well, better type colon this one. Okay. This component is unique. It has to appear. No matter which way you do it, you will come up with this component. Whether the uniqueness of this component we can discuss. But let me draw the pictures. So I'm going to do a computation of pictures. So let's say there's an equation of pictures, and the equation of pictures, this picture is equal to the following intersection of pictures. So I make the picture for x minus y. It's a very easy picture. It just looks like this, one component per degree. So as it says in the advertisement, we get an easy picture for a prime ideal, very homogeneous picture, just degree by degree. And now we need to wrap our head a little bit around the monomial ideal. How do we make the picture for the monomial ideal? We make a connection between any UV that are so that the binomial is in that monomial ideal. But the polynomials in such an ideal, or the binomials in that ideal, are just the binomials such that both monomials are contained in the ideal. So this connects any two monomials that are divisible by this or this. Okay, so I'm going to draw the picture like this. I have 4 isolated dots. I'm just going to draw the picture of monomial ideals. If you have worked with monomial ideals, you know, have seen these pictures. It's just everything here is connected to everything else. Yeah, everybody here is connected to everybody else. All the binomials that are possible in this region are in there. in particular, also x squared minus y squared. Yeah, everybody in this region is connected to everybody else because x squared minus y squared is in here, x cubed minus y to the fifth is in there, everything is in there. So I just make this pattern. And the intersection of these two pictures is this picture accurately as graphs. Okay, so all my tomorrow's lecture will be about the magic of these computations. Why don't we do all our computations with the pictures? Okay, that's for tomorrow. So today I want to show one application from algebraic statistics that had to do with this. Okay, and this is about conditional independence. So how do we make this work? From a paper of mine with Johannes Rau, Jürgen Herzog, Takayuki Hibi, and Freya Reinsted here. And it's the last section in that paper. It's the paper about binomial edge ideals. Some people have maybe studied binomial edge ideals. And in the end of that paper, there's an algebraic statistics application, which almost nobody ever cited. So everybody likes binomial edge ideals because they have a fancy name and lots of combinatorial structure. But so let me tell you about the fifth section of that paper. So in the fifth section of that paper, we do an application to conditional independence ideals. So yesterday we had, in my lecture, there was unconditional independence, and we have seen that for discrete variables, it's described by 2x2 minors. So today we're also going to have more of these 2x2 minors. So there are also parts of conditional independence where also 2x2 minors arise. Sometimes also larger minors, but I'm in the situation of binomial ideals. And this is the same conditional independence as in Carlos' lecture, but here's for discrete variables. So I'm going to still be in the setting of a polynomial ring with variables that are called P sub indices. Okay, so we have random variables. One is called y, and then they're called x1 to xn. So I have n plus 1 random variables. And for simplicity, they take a finite number of states. For simplicity, we can say they are binary. Take finitely many values. Say in 0, 1, 2. So the application that we had in mind when we studied this problem was a probabilistic computation. So what's a probabilistic computation? A probabilistic computation takes x1 to xn as inputs and outputs y in terms of a joint distribution. So, I mean, it's not really a model for computation. It's more a way to think about this collection. So we think x1 to xn are inputs, and y is the output of a probabilistic computation modeled by just a joint distribution. So a joint distribution, like yesterday, is just a collection of elementary probabilities. So there are 2 to the n possible states, and the joint distribution is just going to be a p, which is one of these, one might call them probability tensors, p sub small y, small x1 to small xn, where all of these small y and x1 to xn are all binary. So these are 2 to the n plus 1 numbers that should be non-negative. And if you take the sum over all of them, the result should be 1. And P 0, 0, 0, 0, 0 is just that the probability that x1 is 0, xn is 0, and then y is also 0. So we were working back then with some people who try to design autonomous robots, or like experiment with autonomous robots, and they were interested in these kind of probabilistic computations. And yeah, they had fun. These robot people, they did fun stuff. So I mean, this is just now a story. It has nothing to do with what I'm talking about here mathematically. But they built, I once saw a snake robot that they built. So they built a snake. So snake is just like parts that are this long. You take 7 of these parts and they have a joint and the robot can move the joint. And so the robot had like no programming whatsoever. It was built on information theoretic principles, and the information theoretic principles was that it could measure how much when it tries to move. So it wants to set the joint like this, but maybe if there are some outside forces, maybe if there's a wall or some other creature, it cannot move. So it gives the command, move like this, move your joint like this, and then it either happens or doesn't happen depending on the physics where the robot is situated. So, and then the programming was to use some information theoretic learning algorithm to maximize the effectivity. So the robot should be like as active in its environment as possible. So they did first computer simulations, but cutting to the chase, they even built this thing in the end, and it would solve this optimization problem by learning how to jump. So they put this thing on a flat surface and was like crawling around doing like random things, and then at some point like making these U-shaped bows, and at some point it could jump. It would like do some motion that it would jump and like try to be as active as possible in the air because there were no constraints. Anyway, so the only connection to this story is that's the same people who asked that question. I wish I could have. I mean, imagine writing a grant application after you've done that, yes. And imagine writing a grant application after you, I don't know, can do computation with such pictures. Which one will get funding from the government and which one will get funding from the pure research something part? Okay.
So, can I ask something about?
Sure.
So my colleague is telling me that there's no other component is only explains why. That makes sense.
Can you confirm? Can somebody type this into Macaulay 2 and see if the intersection is right?
Yes, you got it.
It's right. He says it's right. Okay. Okay. So what we wanted to, okay, I haven't told you the question that they asked. So we wanted to understand what kind of distributions satisfy a certain robustness against failure. So our goal was to model that this computation is robust against some of the inputs failing, being broken. And we implemented it with conditional independence. Okay, so want to understand which P are robust against one of the xi failing. So, and now comes, this was the original question, and now our idea was, conditional independence. So why don't we say that y should be independent of xi given all the rest, x1 to xn with xi omitted. I from 1 to n. Okay, so this is Carlos explained it. So y should be independent of one of the inputs, given that all the other inputs are there, or the other inputs are known. So now this becomes an algebraic question. This is the skill, is a very important skill if one wants to do applied mathematics, to talk to the robot people and see that they have a question about varieties. Yes, the robot people ask which computations are robust against failure, and then you play around with it and you see, oh, we could use conditional independence, and then you read in the textbook by Seth Sullivan, or you learn in Carlos' lecture that this is actually an algebraic condition. Algebraic condition. I will write out one of the ideals. So ideal of y independent of xi given, I just write rest here. It's generated by quadratic polynomials, and they look like this. P y x1 to the xn. So it's going to be a 2x2 minor of a tensor. So we are going to be in one specific two-dimensional slice, and then we're going to do a 2x2 minor. So maybe you recognize it once I've fully written it out. Times those quadratic polynomial 2x2 minor y prime x1 to, and then xi prime to xn. So now it's the same except the y and the xi have a prime, and the other term is there's one prime here and one prime here. So p y prime x1 to xn times p y x1 to xi prime xn. So this is a 2x2 minor. And so in general, condition Ci is defined by binomials if all variables appear in the statement. So here we have the property that each y is here, xi is here, and all the other ones are here. If I had y is independent of x1 given x2, and then the others don't appear, I get more complicated polynomials. But if all the variables appear in the statement, it's going to be such a binomial ideal. Okay, so let's do the easiest example over here, maybe, so that we can kind of keep track of what's going on. So the easiest example is 2 inputs, 1 output. So we have p's with 3 indices. Example, n equals 2. So we have just 2 statements. Y is independent of x1 given x2, and y is independent of x2 given x1. Here I gave you only one of these ideals. Of course, I want all of these statements to hold simultaneously. Yes, so this is like, it should be, the system should be robust against failure of any input. I could also model other questions with this. So what I'm going to do is I'm going to intersect the varieties of this and take the sum of these ideals. So this is the ideal for one statement. I have to take the sum of such ideals. So the variety of one such I is in fact a toric variety. So that's a prime ideal. Y intersection of x I given rest is toric, but we intersect. For I from 1 to n. Okay, so here we have I y independent of x1 given x2 is generated by, okay, I take p y. There's also some quantifiers missing. I will add them soon. P y x1 x2 times p y prime x1 prime x2 minus p y. I should probably give the. Okay, there's only 2 polynomials, so I write them out and then we do the pattern matching. So p0 0 0 times p1 1 0 minus p1 0 0 p 0, 1, 0. So that's a polynomial. It's a 2 by 2 minor, and the last entry is always 0. And here it does the 2 by 2 minor thing. 0, 0, 1, 1. This is like these two minus these two. This is how 2 by 2 minor works. And this one is fixed. And we need the same thing for the second one, fixed to 1. So that's the first one. For the second one, you do the 2 by 2 minor thing on the first and the third entry and keep the middle one fixed. You always keep the ones fixed that are in this conditioning set, and you do the 2 by 2 minor thing on those. And so this is here for all y, y prime, xi, xi prime, and so on in 0, 1 to the, yeah, 0, 1. Yeah, so the other ones only remain ones, and the ones that are independent appear twice because you have to take the 0 and the 1. Okay. This one is conditioned on x2. Yeah, 2 is the third entry. x2 is the third entry because y comes first in my notation. Okay. Well, y always comes first, yes? No, Carlos was worried about there's a 2 here, and so he was looking in the second index because that's how it happens when you have x1 to xn. But here is, I should maybe call it x0 or do something else. Okay. Y comes first, and that's why the 2 is in the third position. Okay, now what can we do? We want to understand this variety, the intersection of these toric varieties. So we do the primary decomposition. Okay. Do the primary decomposition of this ideal I, the sum over these ideals I, y independent of xi given rest for I from 1 to, yeah, just throw all the generators in one big pot, then you get a non-prime ideal, you do the decomposition, and you get some components. Okay, so the then so now I back in that time I implemented some algorithms for binomial primary decomposition. So this good thing is binomial primary decomposition is faster than general primary decomposition. General primary decomposition is a very complicated algorithm. It's good to, if you want to understand how computer algebra actually works, studying primary decomposition algorithms or factorization algorithms is a very good topic to study. And in binomial primary decomposition is a more combinatorial procedure. More on that tomorrow. But you stare at the result for a while, stare at examples long enough, and use general theory of Eisenbart and Sturmfeld, theory of Eisenbart and Sturmfeld, tell you there's only one component. There's but one component which contains strictly positive P. P with P, Y, X1 to Xn positive. Okay, so there's this zoo of components, and only one can have positive entries. And now we are in the lucky situation. So you get a bunch of polynomials, and you have to say what they mean. And we got lucky, so they mean something. It can also happen that they don't mean something, but here they mean something, and they mean total independence. You can interpret them. Well, let's put that as a theorem. I think it's a nice insight. A theorem, if P is positive, then Y is independent of all of the inputs, X1 to Xn, given nothing. So the only way a strictly positive distribution can satisfy all of these constraints is if you have if there's no computation at all. The output is completely independent of the input. Actually, not all this machinery of the decompositions was necessary to get this part of the result, because there's also one of the axioms, the intersection axiom, that holds for conditional independence, which also gives this. But for what comes next, we do the decomposition. So Y is unconditionally independent of the inputs x1 to xn. So what this taught us is that anytime you want to do such a robust computation, the robust computation will exploit features of the input. So if this if there's some zeros in this distribution, if some of these p's are zeros, that could, for instance, happen because some of the input combinations are not possible. Okay, so it will never happen that x1 and x2 are both 0 at the same time, because that has a probability 0. If there's such a pattern, the computation can exploit it and create the robustness by exploiting that. So the remaining components show how to exploit patterns in the input. So let's see what this means in this example. So in this example, we turns out 3 components. So here's computation, you type the other ideal, you take the sum, you do primary decomposition, and you get 3 components. One is, as we already said, is Y is independent of x1 and x2. And the second component doesn't have a conditional independence interpretation, but I'd show you the equations. So the equations are, and then you tell me what they are. P0, is equal to, so 4 of the 8 probabilities are 0. P11 is 0. P111 is 0. And P100 is 0. That's the second component. Wait. This one I already had. Sorry. I need P011. Okay, 000, 100, 011, and 111. And 3 is, and no further constraints. Just these zeros, no further constraints. No binomial constraints are left, just these constraints. And then P, the other one, I should be able to make it automatically, yes. P10, P001, and P110, P101 equals 0. So I give you a moment to stare at this. This is a very important part that you need to practice. Computer algebra is so fast that staring at the input always takes exponentially longer than the computation. Staring at the output. Staring at the input also takes very long sometimes. Creating the input. Okay, what you should read is these things cannot occur, yeah? So in the input, the system is never in a state where these happens and only the other. So these are all the 8 states appear here. So in this situation, only the ones, these 4 appear. And in this situation, only the top ones appear and the other ones are 0. Any guesses? What do they mean? The computation is done now. Primary decomposition was fast. And you get these 2 constraints, the components. Yeah, go ahead.
Second argument, x1 can't equal x2. got the same.
Exactly. So here the observation is here. No matter what the output is, the output could be 0 or 1. The x2 and x1 are the same. Actually, here in the top, these are the ones that are 0. So here means they're always different. x1 and x2 are always different in this component. And here in this third component, x2 and x1 are always the same. So, and that's now it all makes sense. So the computation is robust against one failure if the other one is just a copy of the first. If both are the same, then if you remove one, no information is lost. If both are always different, the same. If you remove one, the other one is always lost. You can reconstruct it because you know that one is either the same. So in this kind of information, you now get out of the primary decomposition. So in general, there is a zoo of things going on, different combinations. So let me give you just the theorem that summarizes it without saying details about specific examples. So there always exists a partition of the inputs of the 2 to the n inputs into blocks B, such that P has the following form: Py x1 to xn is. So there's a probability of being in that block, and then a conditional probability of the output that only depends on which block you're in, and not what the particular input in the block is. So I write it like this: P of y given B. Yeah, so that's a distribution over blocks, and then an output probability that only depends on the block, not what the specific input in the block is. If x1 to xn is in B, or 0 if x1 to xn is in none of the blocks. In no block. Okay, so that's basically the only structural insight that you can derive in general. And then if you're interested in a specific situation, you can, of course, analyze it further. Okay, so that's my little application. And so now I have 5 minutes maybe to outline some of the learnings, I think, and some of the problems that we could derive from this. And I've grouped it a bit in different classes. And there are some explicit references in the PDF. Okay, so how to find problems. Okay, so number one, I recommend always is number one, go to talks. Okay, so you go to talks, you listen to the talks, and of course you have to pay attention and find your math structure in some other area. Try to, yes. It's not easy. This is the hardest of the problems. So other area could be mathematics, but sometimes also biology. So if you go to a colloquium, also you go to the natural sciences colloquia, sometimes you're lucky. And of course it takes lots of talks before you hit the gold mine. But once you hit the gold mine, you can get all the gold. So what I look for is binomial ideals. Yes, so this is I look for binomial ideals. I look for primary decomposition, generally polynomial equations. I think where the new thing happens with algebra, particular, is when somehow people doing numerics and doing applied mathematics with the computer in the classical sense, doing approximation during numerics, have already been there and solved some of the problems, then there are usually some corner cases where the practitioners know, yeah, okay, if that derivative vanishes, then that method somehow doesn't work. And then they moved on. And I think these are often cases where algebra can give an exact answer. Why does the method not work in this case? And what can be done about it? Usually it's because some implicit algebraic structure was there and can somehow be exploited. Okay, so this is the field of nonlinear algebra. So Bernd Sturmfeld coined this term nonlinear algebra to somehow transport the idea that we know that linear algebra is extremely successful. Yes, the computers here, they do linear algebra all the time. It's like to do all the things that make our modern life possible, we exploit linear algebra. And now in the 21st century, nonlinear algebra can move to the same level. So polynomials are finally getting their part of the show. Okay, so 2, if you like pure algebra, ask algebraic questions about objects from applications. Yeah, so we have many concepts in algebra. You have you can ask the regularity. It really, so this is what mathematics is good at. There's some class of objects, and we classify it. We understand every little corner of it, and that's always valuable work to understand. Like, you take conditional independence ideals for discrete random variables, and you ask, okay, there's this primary decomposition. Are they always radical? Yeah, can you find a conditional independence idea that's not a radical idea? So we did in the beginning these experiments. So these are radical. These are always radical. Yeah, so you can we show in the paper that they're always radical. They have a square-free Grübner basis even. So that's solved. Except that it's not true. If you make a complicated enough conditional independence ideal, it can be non-radical. And then it's also interesting question what this means. Yeah, you combine a bunch of conditional independence constraints, and you get something that has multiplicity. Is there any statistics interpretation of this? I don't know of any. By the way, the proof that this is non-radical could not be carried out with computer algebra because you couldn't compute a Gröbner basis and do a classic radicality check. When I found this example of a non-radical conditional independence ideal, I confirmed it using a lattice walk. So I found a binomial that's like not in there, but the square is in there. And I did this with like walking on lattice points because a Gröbner basis of that idea would not be available. Okay, so then even more specific, understand. Now it comes more like to my to-do list. Understand binomial ideal decompositions. So one problem that I'm very interested in, and is my long-term, is my career problem, is to understand which intersections, what characterizes intersections of binomial ideals. So what you can have is, if you have a binomial ideal, you decompose it, and you get over an algebraically closed field, Eisenbach-Sturmfeld's theorem, you get binomial ideals. You primarily decompose it into binomial ideals. But if you take any binomial ideals, you intersect them, you're never going to get a binomial ideal. This is like very rare. Yeah, you multiply 2 binomials, you get a polynomial with 4 terms because that's what happens. Yes, so 2 terms times 2 terms gives 4 terms. So what kind of cancellation? So for individual polynomials, you can somehow understand it with Newton polytopes and so. But on the level of ideals, what makes an intersection of binomial ideals binomial, or which other non-binomial ideals have a primary decomposition into binomial ideals? I think these are some problems I work on, And okay, I have one fourth problem. Yeah, there's a fourth and a fifth problem that are very specific. Problem 17.17 in some old paper, but you can read it yourself and ask me about it. So thank you very much.
Are there any questions from the audience? Seemingly there are no. I think the crux of these lectures have been described in this particular board. So good advice for the youngsters who are interested in working in this particular direction. Thank you, Thomas. Now we are heading toward the second talk of this session. Carlos Amendola will continue on building on the keywords he started from the previous lecture.